So this is a tutorial session for week 5. So I'm going to take you through the tutorial sheet. So first of all, let me show you the tutorial sheet if you haven't seen it before. Um, the tutorial sheet is let me open this, guys. The tutorial sheet, you can find it on the course website. So if you go to week 5, which is this one, and click on the sheet. All right, this is the tutorial sheet for today. All right. Now, as usual, I will take you through line by line, and also there are five exercises at the very end. I will try to do as many of them as I can, depending on the time. Right. Okay, guys. So first, let's go back to the first page. All right, this is page 1. Now, this tutorial is about working with distributions. Right. The R has many distributions. That nearly all the distributions that you will encounter in your lifetime are contained in R. So there are some which are discrete, and there are some which are continuous. So these are some of the discrete distributions in R, and these are some of the continuous distributions in R. So for example, binomial is discrete. So for every distribution, there is an abbreviation in R. So binomial is abbreviated as BINOM. Poisson is abbreviated as POIS. The uniform is abbreviated as UNIF. Normal, NORM. Exponential, EXP, and so on. All right, now for any given distribution, there are 4 commands: the D name command, the P name command, the Q name command, the R name command. So the D followed by the name of the distribution will compute the density of the PMF, depending on whether the distribution is continuous or discrete. P followed by the name of the distribution will compute the CDF, or the probabilities associated with the distribution. Q followed by the name will compute the quantiles associated with the distribution. And R followed by the name of the distribution will generate random numbers from the distribution. So for example, if you take the normal, remember the normal is abbreviated as NORM. D norm will compute the density of the normal. P norm will compute the probabilities of normal. Q norm will compute the quantiles of the normal distribution, and R norm will generate random numbers from a normal distribution, right? So these D, P, Q, R apply to any distribution, whether it's discrete or continuous, right? So it's very convenient. So it's like if you want to compute the density or the probabilities or the quantiles or the random numbers, you can use R, right? It's very convenient. All right, so let me go back to the website. As usual, if you have any comments, if you have comments, please feel free to use the chat room. All right. I really want you to give me as many comments as possible so that you understand things better. All right, I just opened R. So I'm going to take you through line by line. So the first thing I'm going to show you is how to plot the PMF of a binomial distribution. So I'm going to define X as a sequence from 0 to 50 in steps of 1. So X are these values, right? Then I'm going to compute Y as, I'm going to compute Y as the density of the binomial at X with, remember, the binomial has 2 parameters, the size parameter, let me take it to be 50, the probability parameter, which let me take it to be 0.6. Now, if you plot X comma Y, this is what you will get. Excuse me. And you see this, guys. So this is the plot of the probability mass function of a binomial with parameters 50 and 0.6. Right? If you like, you can join the points together using type equal to L. Is L for line, right? So it will look like this, right? You shouldn't confuse L with 1. This guy here is L, not 1, right? Although they look similar, right? Okay. Now let me show you how to compute the PMF. Now suppose X is a binomial variable with parameters say 50 and 0.6. And suppose you want to find the probability that X equals to say 35, right? Now to do this in R, to find this probability in R, you just type D binom, right, at 35, size equal to 50, and probability equal to 0.6. All right, so the value, the probability is 0.0415, etc. Right? Okay, now suppose you want to find the probability, say X is less than or equal to 25, right? Okay, the way to do this in R is as follows. You use the command pbinom. Remember, pbinom computes the probabilities associated with binomial. You say pbinom at 25 will compute the probability that X is less than or equal to 25. Okay, now suppose you want to find the probability that X is between, say, 20 and 30. Right, now to do things like this, what you need to first rewrite this probability as, remember, binomial is a discrete random variable. It can only take integer values. So the probability that X is between 20 and 30 is the difference of these two probabilities, right? So it will be 30, the probability at 30 minus the probability at 19. All right, so this is the answer. The probability that X is between 20 and 30 is 0.552, etc. So you see what I've done. I've taken 19 here, but not 20. The reason for that is, if you want all the numbers between 20 and 30, you should take away the probability X less than or equal to 30. From that, you should take away the probability that X is less than or equal to 19. You follow me, guys, or not? I mean, but please, if you have any questions, use the chat room, okay? All right, now suppose you want to find the quantiles of the binomial. So suppose you want the median. Remember, the median is the halfway point, so probability is 0.5. Okay, so this was the median of the binomial with parameters 50 and 0.6. And this is the first quartile of the binomial with parameters 50 and 0.6. And this is the third quartile of a binomial with parameters 50 and 0.6. Finally, let me show you how to use the R binom command. R is, as I said before, is a random number command. So for example, if you type this, yeah, good. D, okay, D stands for Cameron's, for the density. D stands for the density. P stands for probabilities. Q stands for quantile. And R stands for random, right? So it's easy, it's not difficult to remember. Okay. All right. So R, when you type R binom, it generates 5 random numbers from a binomial with parameters 50 and 0.6. So every time you type, excuse me, Every time you type this, you get different numbers because they are random. So the random numbers will be different every time you generate, all right? Okay, guys. All right, so that's on binomial. The next thing I'm going to talk about is the same thing for um, a continuous distribution. Remember from your probability 1 course last semester, the most popular continuous distribution is the normal distribution. So let me show you. So if you type dnorm will compute the density of a normal. So what I have typed here is the density of the normal at 0 when the two parameters, remember there are two parameters for the normal distribution, the mean and the standard deviation. In this case, I did not specify what the mean and the standard deviation are. And in this, if you don't specify what they are, R will take them to be 0 and 1 respectively, which corresponds to the standard normal case. Remember, right, N01 is the standard normal. All right, it's the standard normal case. So if you don't specify the mean or the SD, standard deviation, right, R will assume that the mean is 0 and the standard deviation is 1, right? Okay, but if you do specify them, like here, for example, you should say mean is, say, 4, standard deviation is 10, then this is the value, the density of a normal variable at 0 when it has mean 4 and standard deviation 10 is equal to 0.0368, etc. What does the leading 0 denote? What do you mean? I don't understand you, Joe. What does that leading 0 denote? Which 0 do you mean, Joe? The 0, okay, the 0 here. Do you mean the, all right, okay. Dnorm, okay, this 0 here, all right, means is the density of a variable at 0, right? So like if you have the density function of a normal random variable and you want to compute it at 0, then you put dnorm in brackets 0, right? So that's what I mean, Joe. You should know what I'm saying. Okay, thank you. All right, the next thing I want to talk about is how to plot the density of a normal random variable. So let me take x to be a sequence from -26 to 34, say in steps of 0.1, right? And y to be the density of the normal at x with mean equal to 4, standard deviation equal to 10. Then you should type plot x comma y. This is what you will get. You see, I mean, this you must be familiar with this shape, right? This is the typical shape of a normal density, right? Okay, now if you like, you can join the points by a line, and this is what you will get, right? So this is a smooth version of the density of normal, right? Okay, guys, right. Now let me show you now how to compute the probabilities associated with the normal. All right, so suppose you want to find the probability that x is less than equal to 4, right? And to do this in R, you type Qnorm 4 with mean equal to 4 and SD equal to 10, right? This will compute that, okay? Now, you can also have multiple arguments. So for example, if you type like this, you will get 3 different numbers or 3 different probabilities. The first, this one here is the probability that x is less than equal to 4. This one is the probability that x is less than equal to 8. And this is the probability that x is less than equal to 12, right? All right, okay. Right, next, I'm going to show you how to compute the quantile function of a normal random variable. So for example, if you want the quantile of a standard normal, you will type this. So this is the quantile of a standard normal variable with mean 0 and variance 1, right? Now, if you want the quantile of a different normal, like say, for example, of a normal with mean 4 and standard deviation 10, it will be this, right? And if you want the, say, the median of the normal with mean 4 and standard deviation 10, you will get this. If you want the first quartile, you will get this. If you want the third quartile, you will get this, and so on. All right. All right. So please let me know any questions. Please use the chat box, guys. All right. All right. Finally, let me show you how to generate random numbers, right, from a normal distribution. Right. So suppose you want to generate 5 numbers randomly from a normal with mean 4 and standard deviation 10. This is what you will get. So every time you generate, the numbers will be different because they are random, right? Okay, so this is so Qnorm is a command for generating random numbers from a normal distribution, and so the sample size can be anything. I've just chosen to be 5 here, but it can be anything. It can be 1,000, million, 10, and so on, right? All right. The next thing I'm going to talk about. Are you okay so far, guys, or am I going too fast? I mean, please feel free to question me, right? I can, slow down and explain more clearly what I'm doing. All right. Okay. Thank you. All right. So the next thing I'm going to talk about is I'm going to show you how to draw, how to simulate data and draw a histogram, and also how to plot something on top of a histogram. This is something you haven't done yet, right? So the first thing I'm going to do is I'm going to simulate data from a gamma distribution. Remember, you might have done this in your probability 1 course. So what I'm doing here is I'm simulating a data set of size 100 from a gamma distribution with 2 parameters, the shape parameter equal to 100, and the scale parameter equal to 2. So if you type xm, this is the data that I just simulated, right? Now, if you type let's do a histogram with frequency equal to f. And what did I do? Sorry, I didn't type it correctly. All right, this is what you will get. So this is the histogram of the simulated data, right? Now, if you want, you can define the x-axis for the histogram, the limits for the x-axis using the xlim command. So if you type xlim equal to say 280 to say 500, what did I do? That's something weird. All right, let me go back to the frequency. Okay, this is the histogram, right? This is the histogram. The limits of the x-axis in this case are different. So they could be like, say, from 140 to 280 maybe. So let's check them to be 140 to 280. All right, so you see the xlim command here, it defines the limits for the x-axis. So the lower limit of the x-axis is 140, and the upper limit for the x-axis is 280, right? Now, what I'm going to do is I'm going to plot the density of the gamma distribution that I simulated from on top of this histogram. And to do that, let me show you how to do that. The first thing you need to do is you need to define a sequence of numbers between 140 and 280. say in steps of 1, right? And the second thing you need to do is to compute the density of the gamma at x for the given values of the parameters, which are shape equal to, let me see what I used, 102, yeah? So shape equal to 100 and scale equal to 2. And then then use the command lines, not plot, lines, x comma y, say LTY stands for line type, and this is what you will get. So you see now that I have done the histogram, and on top of the histogram, I have plotted the density of the gamma distribution, and they match each other pretty well. And that's what you would expect, because the data, the histogram was generated from a gamma distribution. So therefore, you would expect the gamma density to fit the histogram pretty well. And that's what you see. Okay, now let me show you one other thing. Now, I have plotted here the density of the gamma, but let me also plot on the same graph the density of a normal. Okay, to do that, I'm going to define y as d norm at x. Remember, the normal has two parameters, the mean and st. So I'm going to take the mean to be the mean of the simulated data, right? And the standard deviation to be the standard deviation of the simulated data, right? And then I'm going to do a line plot with the different colors, let's say red or some other color. And you see, this is what you see. So now the graph has two curves. The first curve, the curve in black, is the density of the gamma distribution. The curve in red is the density of a normal distribution, and they're not too far off, right? At the moment, as you can see, they're not too far off. So in this particular case, the normal is not a bad approximation for the simulated data. But that's not true in general. In general, that will not be true. But for this particular data that we simulated, the normal is not a bad approximation, right? Okay. Now to show you that why the normal may not be a good approximation in general, right? Let me repeat. It's not in the problem sheet, but let me repeat what I have done so far for a different distribution. Like say, suppose, all right, let me go back. Suppose I simulate a data of size 100 from an exponential distribution, right? Then suppose I'm going to do a histogram of the data with frequency equal to false, right? This is what I will get, right? Now the limits are here, as you can see, are from 0 to 5 or something, right? Let's say 0 to 6. So I'm going to define the x lim to be from 0 to 6. All right, then I will define x as a sequence of numbers from 0 to 6, say in steps of 0.1, and y as the density of at x with the rate parameter equal to 1. Then plot x comma y. This is what, oh, sorry, not plot. I messed it up. It should have been line, not plot, guys. Excuse me. It's easy to get it wrong. It should be line, not, you see the mistake I made. It should be line, not plot. This is what you get. Now, if you look at this, you see that the exponential PDF or the density is a good approximation for the simulated data, as you can see. Okay, now if you superimpose on top of this the normal PDF, it will look very different. Now let me show you that, right? So what I'm gonna do is I'm gonna compute the normal PDF, right, at x with the mean equal to the mean of the simulated data, the standard deviation equal to the standard deviation of the simulated data, right? Then I'm going to plot the normal PDF on the same graph with, say, a different color. And this is what you get. You see, now the normal PDF is far away from the exponential PDF, and it's also far away from the histogram, right? And it's not a good match. It's no longer a good match to the simulated data. So that's what I said earlier with the previous example. In the previous example, it was a good match, right? Because that was for a particular data set. But now we are considering a different data set simulated from an exponential distribution, right? So here, the normal PDF, which is in red, is not a good approximation to the data, but the exponential is, because the data was simulated from exponential. All right, guys, any questions? So this is the tutorial sheet. Any questions, guys, so far? Talk to me, guys. How to expand the density axis to show the complete line. Yeah, you can do that. Using the ylim command. So, for example, yeah. So let me show you how to do that. If you want to expand the y-axis, you change the y-axis. At the moment, as you can see, the y-axis goes from 0 to 0.7, right? Now, if you want it, say, to go from 0 to, say, 0.9, you can do this like this. So what you do is you go to the hist command and change the y-axis to go from 0 to, say, 0.9. Yeah, right? And then you do the lines as before. You do the lines like this, right? So you can see this, right? And then you compute the density of the normal, and then you do this, all right? Here is look different. Well, here is kind of look weird. I think, sorry, I must have made a mistake. Sorry. Excuse me. Sorry. Let me repeat this again. Come on. Sorry. X, all right, Y. Excuse me. Just a minute, guys. Give me a sec. I just did them. All right. Then lines. Okay. Now you see this here, right? Then you compute the y for this one, and then finally you do the, excuse me, finally you do this, right? So now you see the y-axis is goes from 0 to 0.9, and you can see a fuller picture. You can see a more complete picture of what is happening, because I've changed the y-axis from 0 to 0.9. All right, so this is how you do it. So you use the command ylim, right? All right, guys, any other question? Hello, guys, talk to me, please. Are you okay so far? All right, thank you, guys. All right, so let me go back to the tutorial sheet, which is this one. So I have gone through the tutorial, and there are 5 exercises at the very end. 1, 2, 3, 4, 5. So let me start with exercise 1, which is on the binomial, all right? And so let me start with exercise exercise number 1. So here we have x is assumed to be a binomial distribution with parameters 100 and 0.3, right? And the first part of the question is to find the probability that x is equal to 33. Yeah, to do this in R, use the command dbinom, d binomial, d for density, right? So d density at 33 with the size parameter equal to 100 and the probability parameter equal to 0.3. So this is how you do it. All right, now to compute the probability that x is between 28 and 34, right? You need to first rewrite this. Remember, x is binomial, which means it can only take integer values. So the probability between 28 and 34 is the difference of these two probabilities, right? Okay, so you need to take the difference of the two probabilities. So the first probability you can compute using the Qnorm command at 34, size equal to 100, probability equal to 0.3. The second probability you can compute with Qnorm 27, size equal to 100, probability equal to 0.3. All right, so this is the probability that x is between 28 and 34. You follow me, guys, or not? Let me know if you don't, guys, please. All right, the next question is to find the probability that x is less than 38. Now, remember, x is integer value. So this means it's the same as the probability that x is less than or equal to 37, right? So to compute this probability, you just change this to 37. That's it. So the probability is 0.9469, etc. All right, so that completes part 1 of exercise 1. To do part 2 is about normal approximation, and I did not cover normal approximation in the course, so I will skip part 2, and I will not examine you in normal approximation, so don't worry. There's no need for you to learn about normal approximation. All right, so let's go to exercise 2. Are you okay with exercise 1? Okay, hopefully you're okay with it. So here you have x is a Poisson random variable with lambda equal to 10, right? And the first part is asking you to draw the PMF over the range from 0 to 25. So first you define the range, right, as this. So these are the numbers from 0 to 25. And then you define y as the density of the Poisson distribution at x with the lambda equal to 10. And then you type plot x comma y, and this is what you see. So what I have drawn here is the density of Poisson with lambda equal to 10, right? Right, if you like, you can use type equal to L. You will see a smooth version looking like this, right? Okay, guys, right. The next thing, the next part of the question is to find the probability that x is less than 15. Now, remember, Poisson is also integer value, so this is the probability that x is less than or equal to 14, and this can be computed using the ppoise command, right, with lambda equal to 10. All right, so the probability is 0.916, etc. The next part is asking you to compute the probability that x is greater than or equal to 8. All right, now this you can write as 1 minus the probability that x is less than or equal to 7. All right. Okay, so this is 1 minus p Poisson at 7 with lambda equal to 10. All right. Okay, guys. Okay. Next, we want to find the probability that x is between 6 and 16. Right. Okay, now to compute this, you need to take the difference between the probability that x is less than or equal to 16 and the probability that x is less than or equal to 5, right? So you say p Poisson to compute the first probability, you say P Poisson at 16 lambda equal to 10 minus P Poisson 5 lambda equal to 10. So the probability that x is between 6 and 16 is 0.9058724. All right. And the next second part is asking you to find the lower, upper, and the median quartiles. Remember, to find the quartiles or quantiles, you use the Q Poisson command. So to find the lower quartile, which is the first quartile, it corresponds to a probability of 0.25, right, with lambda equal to 10. So this is the lower quartile of a Poisson with lambda 10. This is the median of a Poisson with lambda 10. And this is the upper quartile or the third quartile of the Poisson with lambda 10. All right, guys, so this completes exercise 2. Are you okay with this? Any questions on exercise 2, guys? Are you okay? Right. Okay, good. All right, let me then move on to exercise number 3. So here we have an exponential. X is an exponential distribution with parameter 0.2. All right. The first thing we want to do is to plot the density of the PDF of X of the random variable over the range from 0 to 25. So you define a sequence from 0 to 25 in steps of 1, and you define y as the density of the exponential, which is dexp at x with parameter 0.2, and then you say plot x comma y. This is what I have drawn here is the density of an exponential distribution with parameter equal to 0.2. Once again, you can use type equal to L if you want to join the points, right? And this is what you will get, all right? All right, guys. The next thing in exercise 3 is to find the probability that x is less than 12. Remember, exponential is a continuous distribution. So x less than is the same as less than or equal to. And similarly, x greater than is the same as greater than or equal to, and so on. All right, so the probability that x is less than 12 is the same as the probability that x is less than or equal to 12. All right, so you use the command px at 12 with parameter 0.2. So that's the answer. All right, the next thing we want to find is the probability that x is greater than 3. And this you can write as 1 minus the probability that x is less than or equal to 3, right? So the answer will be 1 minus p at 3, parameter 0.2. So the answer is 0.5488. Next, we want to find the probability that x is between 4 and 20, right? And this you can write as the difference of these two probabilities. Right, difference of these two probabilities. The first probability you can compute using pxp at 20, parameter 0.2. The second probability you can compute pxp for parameter 0.2. So the answer to the probability is 0.4310. All right, guys, are you following me? Any questions, please feel free to use the chat room, okay? Okay, the second part of question 3 is to find the 20th, 50th, and 80th percentiles. All right, now to find the percentiles or the quantiles, you use the command qexp. So to find the 20th percentile, you say 0.2, with parameter 0.2. So this is the 20th percentile, and this is the 50th percentile, and this is the 80th percentile, and so on. All right. So that completes exercise 3. All right, next I'm going to go to exercise 4. Exercise 4 is on the normal distribution. So I'm assuming that x is a normal variable with parameters, the mean parameter equal to 20 and the variance parameter equal to 7 squared. So the standard deviation is 7. All right, the first part is asking you to plot the density over the region 0 to 40. So you define x as a sequence from 0 to 40 in steps of 1, and then you define y as the density of the normal at x with the mean parameter equal to 20 and the standard deviation parameter 7. Then you say plot x comma y. And this, you must be familiar with this, right? This is the density of the normal distribution, right? Which is, as you know, is bell-shaped, symmetric, and so on, right? So if you join the points by a line, this is what you see, right? Okay, guys, all right. Now, in the first part, we also want to find the probability that x is less than 17. Right, to find this, you just simply use the command Qnorm. Remember, x is less than, it's the same as less than or equal to, because the normal is a continuous distribution, as you know, right? So this is Qnorm at 17 with mean equal to 20, standard deviation is 7. All right, now to find the probability that x is, next part is to find the probability x is greater than 25, which you can write as 1 minus the probability that x is less than or equal to 25, right? So this is 1 minus Qnorm at 25 with mean equal to 20 and standard deviation equal to 7. And the next part is to find the probability that x is between 13 and 27, right? And this you can write as the probability that x is less than or equal to 13, sorry, less than or equal to 27. Take away the probability, it doesn't matter. Okay, less than 27, take away the probability that x is less than or equal to 13. All right, so the first probability on the right hand side can be computed using this command. All right, and the second probability on the right hand side can be computed using this command. So you take the difference and the answer is 0.6826895. So that's the probability that x is between 13 and 27. You guys okay so far? Are you sure? Please feel free to write on the chat room anything you want to know about. All right, so that's the first part. The second part is to find the percentiles of the normal at the 5th percentile, 10th percentile, 90th percentile, and the 95th percentile. Right, to find the percentiles or the quantiles, you use the command Qnorm. So to find the 5th percentile, you say 0.05, mean equal to 20, standard deviation equal to 7. So this is the 5th percentile. To find the 10th percentile, you say 0.1, all right? To find the 90th percentile, say 0.9. To find the 95th percentile, say 0.95. Okay, so these are easy, these are simple commands for computing quantiles or percentiles of a normal distribution, right? Now, there's another way. If you look at part 3 of question 4, there's another way of computing percentiles for a normal. That is to use the following formula. I don't know if I mentioned this in the class or not. If you have a normal variable with parameters mu and sigma squared, then Q of P of x, remember Q of P is the notation I use for denoting the percentile or the quantile. The quantile function of x, right, is the same as the following. You see what I have written here, guys. Hope you can read it. So what I have written here is that if you have a normal variable with parameters mu and sigma squared, then its quantile function, which is is the same as this, which is mu is the mean parameter plus sigma, which is this standard deviation parameter, times the quantile function of the standard normal variable, which is n01. So instead of you can use this formula also to compute the quantiles that we computed earlier here, right? So let me illustrate that. Instead of using these formulas, right, these commands, I'm going to use this formula here to compute the percentiles. So for the first one, where the mean is 20, the standard deviation is 7, and we are looking for the 5th percentile, I will write 20 plus 7 times Qnorm at 0.05. And I don't need to specify the mean or ST, because if, as I said earlier, if I don't specify the mean or ST, R will assume that the mean is 0 and the standard deviation is 1. And this is what you get. You see, this value 8.48 is the same as this value. So both approaches give the same answer, right? And similarly, if you change this to 0.1, you get 11.02, which is the same as this. Right? And if you change this to 0.9, you get 28.970, etc., which is the same as this. And if you change this to 0.95, you get 31.513, which is the same as this. So what I'm saying here is that there are two ways of computing the quantiles of normal. Okay, one way is to use commands like this, right? And another way is to use this formula here. Is to use this formula where mu is the mean, sigma is the standard deviation, right? Okay, so both ways must give you the same answer, right? They should give the same answer, right? Okay, guys, so this is exercise 4. Any questions on that, guys? You want to? Hello, guys, talk to me, please. Are you okay with exercise 4? Yes, you sure? Okay, all right, so there's one more exercise left. There's one more exercise left, which is, I think I've run out of time already, but so the exercise 5 is about using data, and so it's basically, I mean, if you look at you have the tutorial sheet in front of you. So it's basically, let me show you. So exercise 5 is about trying to fit the normal distribution to the data contained in each of these links, right? So for the first data, which is the simulated data, from the simulated data is data simulated from a normal distribution with mean equal to 10 and variance equal to 4, right? So what you need to do is you need to just read the data and draw the histogram, and on top of the histogram you need to plot the density of the normal with parameters 10, and 10 is the mean, and standard deviation 2, right? So I hope you can do that by yourself. I mean, anyway, if you can wait till tomorrow, I will post the full solutions to all the 5 questions, all the 5 exercises. I mean, so I will, tomorrow evening, I will post the full solutions to all 5 exercises. So there will be 2 types of solutions. One is typed solution, and the other will be like video solutions for all the examples. Sorry, all the exercises, right? So, but I'm sure you guys can do it without looking at the solutions. But if you want to look at the solutions, you will see them posted tomorrow evening. Tomorrow is Wednesday, yeah. Yeah, so I will post them tomorrow evening. Okay. All right, guys. So any questions you'd like to ask me now before the end of the tutorial? Anything you want to talk to me about, like about the course or anything like that? Let me remind you the tutorial. Sorry, the quiz number 4 is due on Thursday this week by 10 a.m. All right. So please, if you haven't submitted already, please do so before the deadline of 10 a.m. Right, on Thursday, the 11th of March. Right. Okay. And if you have any questions to do with my course, as you know, you can contact me 24/7 by email, Skype, Zoom, or phone. My home phone number is, I already gave it to you several times. My home phone number is 0161 273 2941. You can call me 24/7 anytime. Okay. All right, guys. So have a good afternoon or good evening, and I will see you shortly, or you will see me shortly. All right. Take care.
Thank you.
Thank you. Bye.